Okay, welcome back. Now the problem I'm going to do, calling acceleration and tension in a string of a falling ball. So we have a string here, pivoted about the end. This is length L. And then we're going to release this and we're going to analyze the acceleration of the ball as the string is coming down, right? And we're also going to analyze what happens to the tension in the string, and we can ask different questions based on this. So initially when the ball is dropped, you have mg and then you have tension T, right? So the initial angular, the initial acceleration of the object, right? You have mg is equal to ma, right? So the initial acceleration of the object is equal to g, right? And initially it doesn't have much of a velocity, so the tension in the string is almost zero, right? So the tension in the string provides the necessary centripetal force, so we have here mv squared over r, but since v is zero, so t initial we can say is zero, right? As the object is falling, right, so the object reaches here, what happens? So let's define this as the angle theta from the vertical, right, theta like this, and then you have here mg, and then you have here tension in the string, right? So then how are we going to break up these forces? So we're going to say, let's break up the mg into two components. One is the component that is opposing the tension, right? And then one is the component of the mg that's causing it to accelerate this way, right? So this is mg. So this one here, if that angle is theta, this is also going to be theta. So this is going to be mg sine of theta. And then this component here is going to be mg cosine of theta, right? So the mg sine of theta is going to cause this to accelerate. We can call that a tangential, the tangential acceleration of the ball along the direction of its motion, right? So this is a tangential. So we can say mg sine of theta is equal to m a tangential, and then mm cancel, so a tangential is equal to g sine of theta, right? So this is kind of like a block being on an incline, theta, right? And then the block is going down, and if there's no friction, the acceleration of the block is equal to g sine of theta, right? So this is going to be the same acceleration. We call this the a tangential because this one also has a centripetal acceleration, right? So the centripetal acceleration is going to be what? So we have the centripetal acceleration is going to be this way, right? So the tension T minus the mg cos theta, right? So the tension T minus mg cos theta, okay, is going to be equal to ma centripetal, right? And then that's going to give you the centripetal acceleration towards the center of the circle, right? Now we can get an expression for the a centripetal because we know we have a centripetal is v final squared over r, and v final is going to be the tangential velocity of the object. We can put that in red. This is going to be v final tangential. Now how do we calculate the final velocity, right? We can do this from simply an energy perspective, right? We can say the potential energy that it has here converts into kinetic energy here. So we can say the initial potential energy, right, is equal to the final kinetic energy. Okay, so what is the initial potential energy? So at any point, I can put my xy axis here at the bottom, at the location of the object, and I can say how far up is the object with respect to where its location is here, right? What is this distance? So if this is the length of the string, this distance here is going to be L cosine of theta, right? So as this thing is going down, the ball is getting lower and lower and lower, right? So the initial position of the ball, as this thing is getting lower, the initial position of the ball, the equation is still L cosine of theta, right? So we can say the initial potential energy is mgh initial, which equals half mv final squared, right? And then h initial is going to be this distance here, L cosine theta, okay? And that's equal to half mv final squared, and then the m and m cancel, v final squared is going to be 2gl cosine theta, okay? So then if we put that final squared velocity into here, that gives us an expression for the tension in the string depending on what the angle is, right? So we have here T minus mg cos theta is equal to m over r, and then v final squared 2g L cosine theta, right? And then the L is the same as the radius of the circle, right? So this is also L. Okay, and then the L and the L cancel. And we have here tension is 3mg cosine theta. Okay, so this gives us an expression for the tension in the string no matter what the position of the object is, right? The tension in the string. Now we can also derive an equation for the total acceleration of the object, right? What is the magnitude of the total acceleration? The sum of this A tangential and A centripetal. So then we can say A centripetal is going to be what? It's going to be V squared over R. So if you square this, well, we already have an expression that's going to be 2gl cosine theta. That is already V squared. Then you divide that by R. Well, R and the L are the same, right? And then L cancel. So A centripetal is equal to 2g cosine theta. And then A tangential is equal to g sine theta. So let's see if that makes sense now. When theta is 90 degrees, that means the object is still up there. What's going to be the answers? Is going to be what? 2g cosine 90, then it's going to be 0, right? Well, that's what we said when we started this problem. We said when it's up here, it's going to have no centripetal acceleration, right? And then what's A tangential going to be? G sine of theta. So then that's going to be just g, right? So that makes sense. Now when the angle theta is equal to 0, right? Then what's going to happen? Then A tangential is going to be g sine of 0. So A tangential is going to be 0. So by the time this thing is all the way down here, it's not accelerating anymore in the horizontal direction, right? Because it's already going at its maximum speed. Then what's the A centripetal going to be? Then it's going to be 2g, and then cosine of 0 is just 1. So it's just going to be 2g. Okay, what's going to be the V final squared? V final squared is going to be equal to 2g L cosine of theta. That's the general equation. So the A centripetal is going to be 2g. That's interesting, right? So it's going to be 19.6 meters per second squared. Okay, why is that? Well, because the V final, when cosine is 0, V final is going to be 2gl, right? Basically, it's falling from here all the way to the bottom, so it's gained a velocity equal to the square root of 2gl. So it's kind of just basically like doing free fall, right? So then if the velocity squared is equal to that, the A centripetal is just equal to V final squared over R. So R is the same as the L. So you can see here why the A centripetal is 2g, right? So therefore, the equation for the total acceleration is going to be what? A total square root of A centripetal squared plus A tangential squared. And then A centripetal is this one, so you square that one. 4g squared cosine squared theta plus then A tangential squared, you square this one. You're going to get here g squared sine squared theta. And we can factor out the g squared, so then the A total is going to be what? Factor out the g squared, you get g square root of, then you get 4 cosine squared plus sine squared, but because cosine squared plus sine squared is 1, I can take one of these cosine squared, combine it with the sine squared, and I can say 1, and then I'll be left with 3 cosine squared. So this is going to be 3 cosine squared theta plus 1. So that's the expression for the total acceleration, right? How about the direction of the total acceleration? Its direction. So how do we give its direction? So if we put this vector, what's happening? As initially this tangential acceleration is larger, right? And the centripetal acceleration is small. If we put this centripetal acceleration like this, the total acceleration will be like this. So this is the angle alpha. Okay? So we usually define an angle alpha, then angle alpha is equal to the angle of the, if this is A tangential and this is A centripetal, we can define an angle alpha, and that angle alpha is the angle that the total acceleration makes with respect to the radial line, right? So we can say here, tangent of alpha is equal to A tangential divided by A centripetal, right? So it's this triangle that you focus on here. This one is A centripetal, this one here is A tangential, and then this is the alpha, right? So then let's see what's going to happen. Okay, for example, let's say this thing has fallen, and then this theta is the theta is 70 degrees. Okay, so what's going to happen? What are the values here? So A centripetal, A total, for example, is going to equal G square root of 3 cosine squared 70 plus 1, okay, per second squared. So that's when the theta is 70 degrees, so it hasn't fallen that much yet. It's only fallen through an angle of 20, right? And then what is the tension in the string? The tension in the string is 3 mg. So let's just say, for the sake of argument, that the mass is 1 kilogram. So it's just going to be 3 times 1 times 9.8 times cosine of 70. Okay? This is the tension in the string, right? So then, now let's calculate A centripetal separately, and then A tangential separately. What's happening here? So, because it hasn't fallen too much, the A tangential is still larger than A centripetal, right? So this vector is larger. So this vector is larger than this vector here, right? So then what's going to happen? When I put this to the tip of this, I'm going to get this angle here. We define this angle as alpha, right? Then what's going to be alpha? We can say tangent of alpha is A tangential over A centripetal. Okay, so we're going to have 9.21 over 6.70. Okay, so then if we look at here, what's going to happen? So if this is 70 degrees, right? This angle is what? From the horizontal. This is the horizontal, right? This angle is what? That angle is going to be 20 degrees, right? So if this angle is 54 from here to here, what does that mean? Well, how many degrees is this angle? In other words, the A total vector, how many degrees below the horizontal is the A total vector? So then we say 54 minus 20, then this angle is going to be 34 degrees, right? Because this whole thing is 54 degrees. You subtract 20 from there, and then you get 34, right? So the vector A total will be 34 degrees below the x-axis, below the horizontal, right? So then what's going to happen as this thing falls a little bit more? Okay? Okay, so if it's fallen a little bit more, something like this, let's say, this is theta, so then the A tangential is now going to be smaller, A centripetal is going to be larger. Okay, why is A centripetal getting larger? Because it's picking up speed. As it picks up speed, A centripetal is V final squared over R, right? It's getting larger, larger, larger. A tangential is getting smaller. So if it goes all the way down here, right? A tangential is now going to be smaller. A centripetal is going to be larger. Okay, so now let's say the theta is equal to, let's say the theta is equal to 20 degrees. What happens? Okay, so now you can see, you're going to see that A centripetal is much larger, right? So then you're going to say, let's recalculate everything with 20 degrees. So now we have here cosine squared 20, and then this is going to be cosine of 20, sine of 20, and then this is going to be cosine of 20. Okay, 0.35. So you see, this is a lot smaller than this guy. This is much, much bigger now. A centripetal, right? So then if I put this to the tip of that, and then I calculate here alpha, alpha is going to be a lot smaller, right? So alpha is going to be, tangent of alpha is A tangential, and A tangential is going to be 3.35 divided by 18.42 degrees, right? So since the centripetal acceleration dominates the acceleration, this angle is very small. So then how many degrees is this above the horizontal? What's this angle? So if this is 20 degrees, right? If this is 20 degrees, how many degrees is this whole thing? So this makes a triangle, right? This is 90 degrees. So this whole thing is going to be 70. So if this little piece is 10.3, how many degrees above the horizontal is the total acceleration, right? So this piece here is going to be what? 70 degrees minus 10.3, right? And that's going to be 59.7 degrees. So now the total acceleration is going to be 59.7 degrees above, right? Above the x-axis, because this whole thing was 70, and then I subtracted alpha from that, right? So can we calculate at which point the total acceleration is actually horizontal? Okay, so what would have to happen? So A tangential would have to be like this, A centripetal would have to be like this, right? A total, when you put this to the tip of that, right? A total is this. So at a certain point, A total can actually point horizontal. What point would that be? Well, if this thing is theta, right, alpha would have to equal to the complementary angle of theta, right? So if alpha is 90 minus theta, what's going to happen? So this is going to be alpha, right? If alpha is 90 minus theta, then the A total will point horizontal because it will exactly look like this. This will go like this. You'll put this to the tip of that. Whatever alpha is, if this is the complementary of that, A total points horizontal. So at what angle will that be? When will that occur? Okay, so then we can say here, E cancel. So I have here tangent alpha is sine of theta, and then I'm going to say theta is equal to 90 minus alpha. Okay, 90 minus alpha over 2 cosine of 90 minus alpha. Okay, it's going to be 1 over 2 tangent of alpha. So then tangent squared alpha is going to be 1/2, and then tangent of alpha is going to be 1 over square root of 2. Okay, so then what is that point? So what does that mean? Well, theta will have to be the complementary to that. So 54.A tangential is going to be 8. And then this is going to be larger. So 11.33. So it looks like that. So this is the better way to draw the pictures, right? So then if you do tangent of alpha is equal to A tangential over A centripetal, 8 over 11.33. So when you do this, 8 divided by 11.33, and you take the inverse tangent, this angle comes out to be, alpha comes out to be 35.3 degrees. You see? Another question we could ask is, at what point is A tangential and A centripetal the same? At which point does that occur? Well, it probably occurred before this point. You see how the A tangential is already smaller? So probably somewhere here, A tangential was already equal to A centripetal. So when does that occur? Okay, so we can say here A centripetal equals A tangential, right? So this is going to be 2g cosine theta. A tangential is g sine theta, and then it's going to be 2 is equal to tangent theta. Okay, now we get theta is equal to 63.43. So that's actually pretty surprising. That means this is 63 degrees, a lot bigger than the 53 degrees, right? 63.4 degrees, and this is only about 27 degrees. That means as this thing falls right away, the tangential acceleration drops, the centripetal acceleration gets large, and the two accelerations are equal to each other. That means the angle between them is 45 degrees, right? But because it is 45, what's going to happen? The tangential acceleration and the centripetal acceleration are the same, so this angle here is going to be 45, but because this is 63 degrees, this piece is going to be 27 degrees. Because 45 is larger than 27, that means this is going to be 18 degrees. That means at that point, even though the two are equal to each other, the total acceleration is not horizontal. Because it occurs so fast, the total acceleration is still pointing down. 45 is larger than 27, so 45 minus 27 gives you 18 degrees, and the total acceleration points below the x-axis. So you can see here quite a bit of geometry, quite a bit of analysis of angles, centripetal acceleration, tangential acceleration, and analyzing the direction of the total acceleration. Thank you very much.